Hi, everyone. Thanks for joining us today. And thank you, Dr. Jim, for accepting our invitation. Dr. Jim Luedtke is a professor and associate chair of graduate affairs at the University of Wisconsin-Madison. He received his Ph.D. in industrial and system engineering at the Georgia Institute of Technology in 2007. He has been awarded the Informs Optimization Society Prize for Young Researchers in 2013. His research interests are mixed integer optimization, stochastic optimization with risk constraint, and application of optimization. And today, Dr. Jim will talk about branch and BranchandCut for stochastic integer programming.
Okay, thank you very much for the nice introduction and for having me join you all. Sorry, it was not so convenient for me to travel there these days, so otherwise I would rather be around and see you all, but maybe someday I'll visit again. Okay, so let me just get into it here. Briefly start with kind of a motivating example for why this class of problem could be interesting. So I'm going to talk about kind of a generation transmission capacity expansion problem in sort of the power grid. And the idea is, you're expecting some increases in power demands. So you're thinking about installing generators in different locations or sizes, and then maybe transmission lines to connect them. And you want to do this, to sort of minimize the expansion costs and the operating costs to meet the demands over time. Okay, so certainly this is a problem that has discrete decisions. Whether or not you install a generator or not is kind of an all or nothing decision. Same with transmission lines. You might have a set of discrete sizes you choose from, but still it's very, very much discrete. And there's definitely a lot of uncertainty, right? At the time you're making these planning decisions, you don't really know how much demand there's going to be in the future 10 years from now, or especially on individual days in the future. And also, with a lot of renewable energy in the grid, another important factor is how much sort of energy is going to be sort of supplied by those, which again is very variable and uncertain. So to just give a very stylistic model that sort of fits this general framework, in particular, I'm going to ignore transmission for the stylistic model, but the ideas are basically the same. So the idea is we have some candidate generators that we're considering installing, this given by G. We have all of our demand locations by the set J. If you install a generator, there's certain fixed costs for that, and it will have a certain capacity. And then in a deterministic model, that's what I start with here, we may imagine that every customer has a given demand DJ. And so you can imagine this demand being for a particular hour, in the future. So sort of consider an arbitrary hour that you need to plan for. And then we have some binary decision variables for whether or not you open each generator. So Xi is 1 if you open generator I and 0 otherwise. And then given those choices, then you're going to try to sort of meet the demands at different locations from different facilities. So Yij will be sort of how much power you send from location J, from facility I to location J. And then we'll assume in this model, and we'll see this is maybe more important later when we talk about possibly having uncertainty, but we'll assume that there's an option to maybe not meet all of the demand at location J, but you will pay a penalty for that. So Zj is going to be sort of recording some amount of shortfall or shed load at a particular customer J. And so the model looks like this. I'm going to go through it pretty quickly because I want to get into the main content here, but basically we're minimizing the installation costs, the sort of transmission or sort of transportation costs, some costs for penalties. For each customer, you either have to sort of send enough from all the facilities, or otherwise you record some shortfall in order to meet its total demand. And for each generator, first of all, if you don't open the generator, so Xi is 0, then this right-hand side will be 0 and says you can't send anything from it. Otherwise, if you do open it, then the maximum capacity is Ci, and this controls that you can't send more than you can produce. And so we have the binary restrictions and these sort of non-negativity on the variables. Now, in sort of stochastic programming, we think about things might be uncertain. Okay, and so, in particular in this application, the demand certainly might be uncertain, and also the capacities could be uncertain. So that's the way you can think about wind power or solar power or other renewables where the capacity depends on random effects of the weather for that particular time of day. And so, in the two-stage stochastic optimization framework, we sort of break our decisions into one set that are known as the here and now decisions. You have to make those decisions before knowing what the uncertain outcomes are going to be. So you choose those and fix those. That's the first step. Then you're going to observe the random outcomes. So you see what actually happens. And then after observing that, you're allowed to make some recourse actions in response to the observed random variables. And so that's oftentimes called the second stage. And so your goal in this setting is to choose your current decisions so that you minimize the total immediate costs plus, let's say, the expected value of the best response decisions after observing the random stuff here. So I have to say, expected value, because somehow we have all this distribution of possible things that can happen on the random variables, and you have to summarize that in some summary statistic. Commonly, expected value is used there, but certainly you could think of other risk-averse objectives. But for today, I'm just going to focus on sort of the average case here. Okay, so in creating such a model, you somehow have to divide your decision variables into some that have to be made ahead of time. Those are the here and now decisions, and some that can be wait and chosen after observing the random outcomes. So in this sort of generation expansion model, we have the random, the loads could be random. So we're going to imagine that those now are random variables. And as I mentioned, the capacities can also be random variables. We have our same sort of decision variables, except now we're going to categorize that the opening decision, so installing the capacity, those are here and now decisions. We have to choose that once and for all, and it's kind of fixed for our planning horizon. But in terms of how you actually use the installed capacity to meet the demands, that you can wait and see. You can sort of observe what your actual demands are and then kind of do the best you can with that. And so the YIJ variables for that and the amount of sort of unmet demand, those are going to be recourse variables. So the way this model looks then is we're going to sort of minimize our immediate costs from installing these things. We have that first term there. And then we're going to have a second term that's the expected value of the kind of best response given that fixed X. And then once we observe some demands and some capacity levels. Okay, so this Q function here tells us kind of the value of the best response. And so for any given first stage vector X, set of observations of the demands and set of observations of the capacities, we then sort of solve that second stage problem of minimizing the cost to make these meet all the demands or have some load shedding. And then we have sort of these same constraints that we had in the original model, but now they're part of this kind of recourse model here. So that's the two-stage model there. And so generically, what this looks like in a two-stage stochastic integer programming model is you're always going to have some first stage decisions X. Some might be integer constraints, some continuous. We'll assume that for simplicity here, it's all linear constraints. You have some first stage costs and you have expected recourse costs, where the recourse, in general, this sort of counts for all the data that could show up in the recourse subproblem. So it could be the objective function, right-hand side, and the constraint matrices. And sort of generically, we have some recourse actions, which again, also might have some continuous variables and some integer variables. And then we're minimizing sort of the cost of that recourse, where here in this problem, again, the first stage constraints are fixed so that these constraints kind of get moved to the right-hand side, and you have some of these constraints here. And so we'll talk about some special cases where some of these variables are, some subsets of these variables might not be there. So in particular, we're going to spend a lot of time talking about the much simpler case where the recourse problem only has continuous variables. So P2 is 0 there. And so that's somehow much easier to analyze and also serves as the basis for more complex ones. So actually, I would just pause for a second and just say, I do encourage people to go ahead and interrupt with questions, or you could try the chat. I have two screens, so there's a good chance I'll actually be able to see it. And so go ahead and ask questions as you have them. Okay, so we have the class of problems, stochastic integer programming. I hope it's sort of easy to see that there's many possible applications of this problem class. It combines sort of the modeling power of both stochastic uncertainty and also discrete decisions, but it also sort of combines those challenges together. And so in terms of the stochastic programming side of things, there's a huge challenge in just evaluating the expected value. So even given a first stage solution, just estimating the expected value of the recourse options is generally challenging. And then even if you use some kind of a scenario approximation, which I'll talk about very briefly here, that still could be very large size to handle. So that's some challenges that are inherent to the fact that you have uncertainty in your model. Then in integer programming, we just have, typically, we have lots of discrete decisions. So all the combinations of possible decisions leads to an explosion in the number of solutions you have to search through. And so that's, challenge number one. The other thing is somehow, eventually you're going to sort of use some sort of a relaxation approach to approximate this, say linear programming relaxations. But a major challenge there is if your relaxation is weak, and somehow the optimal value is not close to the true integer optimal value, then you can have sort of huge search trees for searching for these problems. So these are the types of challenges we have to deal with, both of these together to be able to solve these stochastic integer programming problems. So just a quick overview of some of the things we'll look at. Okay, I just see the question here. Maybe, Farnaz, can you maybe just ask the question out loud? I might understand it better that way.
Hi, yes. So there is a parameter that you call it PJ, ZJ, that, yes, as a penalizing that if it's not going to be reached that expected value. Yep. So these PJs are also constant or also depend on, for example, the opening or the amount of the demand?
Okay, so yeah, in the model I've written down as an example, they're constants. They certainly could be dependent on, they could be random, and so they could depend on other factors like the demands and things like that. So it would be a very easy extension to have them, the modeling framework certainly allows them to be random and dependent with all the other random things there is completely fine. But it would not be, the stochastic programming framework that I'm looking at here would not allow to have those PJs be dependent on the decision variables. And so that's a different class of model known as decision-dependent uncertainty, which is very interesting. And there's lots of models where that's a useful thing to have, but that would not be something that would be directly sort of solvable with the methods I'll talk about today.
Yes, thank you.
Okay, so, and then Beirang's asking about the, so I think, Beirang, I think we'll see something a little bit about this here, where there is an extensive model that we can build after we sort of do some kind of scenario approximation, but it's going to be very large scale, and so we'll have to talk about how to solve that. But in a certain sense, but the key issue in terms of the general modeling aspect here is that you definitely have some decisions that you must fix without knowing the certain values, and then you have other decisions that can be different for every possible value of the uncertainty. Those are those recourse decisions, and it's really important to know which is which, because these here and now decisions, there's only one set of those. You must fix those. These other ones can vary with the uncertainty, and so you have to sort of divide it that way. Okay. So let me sort of move on to sort of the overview of the tutorial then. So very briefly, I'm going to talk about sort of approximating this expected value via an approach that's known as sample average approximation. I'm asked to focus on either the branch and BranchandCut method, so I'm going to spend the most time on that. But in terms of using it for stochastic integer programming, it's very important to understand that, this is for solving an approximation of some problem that probably is not the exact problem you're trying to solve. And it's really important to understand, a little bit about, how to use that approximation appropriately. And so then we'll move on to sort of the methods for solving that approximation, this sample average approximation. And if I have time, I can talk about a little bit of recent developments as well. So in terms of, the approximating to expected value. So in general, we have this random vector C is typically could be high dimensional. I mean, if it were just one dimensional, then the expected value wouldn't be necessarily so hard to calculate. But in typical applications, you can think about you're going to have demands at lots of locations. You're going to have capacities or how much solar you're going to get for lots of different locations. So it's a high dimensional random vector, and sort of evaluating that as a high dimensional integral. It's not something that can be done directly at high accuracy. And then the other challenge is that that's just for a single fixed x, right? But really, we're going to be optimizing over different possible values of x. And so we need to have a way to approximate this over many different values of x. So the very, very simple idea, sort of a natural generalization of sort of just Monte Carlo estimation. The idea is you just take a Monte Carlo sample of your random vector C. So CS is a sample for the whole vector of all the outcomes jointly. For all the different scenarios, 1 up to capital S would be the number of scenarios that we've created in this sample. And then the idea is where you have this expected value showing up, you just replace that with a sample average over this finite set of scenarios. Okay, so that's sort of simple thing any engineer might think to do. And then the question is how does it work? Right. So, once you've done this now becomes a deterministic problem because you just have this finite list of scenarios. It's a finite sum objective, and we'll talk about how to solve that large scale optimization model. But the question is, could you expect this to work? It seems kind of unbelievable that it might. And so really, it's not just a matter of, could it work with a huge number of scenarios, but it also should somehow work and give a good approximation with the number of scenarios that's not too large. Okay, so naturally, there's a whole lot of research that goes into studying this question. And at a very high level, in a wide variety of problem settings, including integer settings, is importantly for this talk today, is that roughly, if you want to have sort of a solution that's somehow epsilon accurate, then the number of scenarios you need in your sample average approximation is going to scale with the two main parameters I'll focus on here is the number of decision variables in the first stage, that's N1, or say N1 plus P1, so the total number of decision variables in the first stage. And it scales linearly with that. So that's actually the good news, is it's the number of scenarios is growing, say, mildly with the number of decision variables. And it doesn't have a very strong explicit dependence even on the number of random variables at all, which is quite surprising. But the bad news is, and this is just a limitation because it's sort of a Monte Carlo sampling approach, is this 1 over epsilon squared term here means that if you want to have high accuracy, then the number of samples is very, very large. And so basically, the conclusion I would draw from this is that if you're willing to accept just modest accuracy, as long as you don't try to drive epsilon too small, then the sample average approximation will work to get you sort of reasonably good solutions. But it's probably not going to work to get extremely, highly precise solutions. I would add my own sort of editorial comment about that is that in this context of stochastic, optimization models, I don't think that obtaining very high accuracy solutions is a very important goal, to be honest. The reason is because these models have so many sort of model errors built into them. You have to model the stochastic sort of random variables. You have many other sort of just general modeling approximations. And so in this kind of context, trying to ask for an extremely highly accurate solution, doesn't necessarily make so much sense as it might make in different contexts. And so in that sense, I think this sample average approximation is sort of good news is that you can get, sort of reasonable approximations with reasonable sample size. A couple just really important, details about if you're going to use sample average approximation. So first of all, it's kind of a randomized algorithm. You take a random sample and then you solve the problem, you get a solution, and that solution itself is random because it depended on your random sample. And so one important thing is just interpreting the output of the solution. So say you get this some solution out of this SAA problem. It's going to be very important that after you have that solution, that you then go and evaluate the solution on a new sample, sort of independent sample of what you used to generate the solution. And don't just use the optimal value from the SAA problem as your estimate of the solution quality, because it turns out there's a bias introduced in that process. Because what happened is you optimized very much to that sample. And so you're going to be overly optimistic about the quality of the solution you get. It's easily sort of fixed by just taking a new independent sample, evaluate it on that different sample, and now you've removed that bias. But it's very important to take that step. The other thing is that if you want to get sort of estimates of the actual sort of optimality gap, how good are your solutions relative to the optimal for the underlying true problem, what you can do is actually solve multiple sample average approximation problems with different samples, and then sort of use the results of that to build a statistical estimate of the optimality gap. So I'm not going to the details of that at all, but just suffice it to say that sort of replication of this process can be used to get sort of valid estimates of the true optimal value. And so, if you think about using this, just look up the relevant papers. You see some of the citations up here to make sure you're sort of using the right approach here. Okay, so that's as much as I'm going to say. Okay, sorry, I just saw a question there in the chat. So this question of how to use historical data for estimating the models is a very, very good question. It basically, I mean, it's a whole matter of statistical sort of, analysis, right? You have your historical data, you somehow then need to use that to build a stochastic model. And that's a whole sort of talk on its own, right? So we'll assume that somehow somebody has built the stochastic model for us, and we can generate samples from that. But absolutely, it makes sense that you would use historical data to do that. Okay, so once we've done this say sample average approximation, from now on, I'm going to be talking about solving a problem where we have just a finite list of scenarios. Okay, so what the problem looks like in this case is I'll just use S for my scenario indices, and now I'm minimizing my first stage cost plus this kind of sample average of the value functions for all of the scenarios that I've seen. Okay, so now it's a finite list of scenarios, but this is otherwise the same kind of structure I've seen before. And the first thing that you can do in this setting is you can introduce for every one of your scenarios. Remember, we have sort of these first stage variables X, which is there's just one set of those variables, of course. But for what you can do is for every one of these scenarios, you can sort of introduce explicitly into your model a different vector of recourse decision variables called YS that says, well, this is what I would do if scenario S occurs. And so if I introduce those variables into my model, then I can sort of write down the constraints that connect those to my first stage decisions. So I just put that into my model. And I put this all together, and now my recourse costs are sort of explicitly written into this model as well. And what I have here is just one really large integer programming model that's equivalent to that stochastic integer program. Okay, so going to this finite list of scenarios bought me a lot, because now I can write down just the single mixed integer program that I could directly load to my favorite solver, Gurobi or Cplex or Express, and just say go. Okay, so this is certainly always the first thing you should try to do if you're trying to solve a stochastic integer program. And so, for example, in this generator expansion problem, this is what that would look like. Basically, what I've done is I just take all of my kind of recourse constraints. All of the variables that are recourse variables now get this index S, sort of saying, okay, that's what I would do if I'm in scenario S. And then I have, DSJ is the demand that I see in scenario S. And then I have these constraints that link it to the first stage variables. Again, I just repeat this for all the scenarios because some of these variables are indexed by S. And then my objective now is I'm sort of averaging my second stage cost over all the different sort of scenarios that occurs there. Okay, so I could just load that to my solver and say go. And the advantage of that is it's straightforward to implement, right? If I can model the deterministic version of my problem, I can certainly model the stochastic version once I have those scenarios. And the second thing is that the state-of-the-art MIP solvers are just getting better and better at solving very large problems. And as they continue to get better, this approach is just going to get better as well. And so it tends to actually, you know, in many problems, as long as the problem size just isn't too big, it often is the best approach. So everything else that I'll talk to you about, you know, the rest of today, you wouldn't need to bother with because just, you know, give this big formulation to the MIP solver is going to be better anyway in those cases. But it does still hit a limit, right? So if the size of your underlying problem or the number of scenarios grows too much, then, you know, there's still going to be just a limit, you know, just in terms of loading this whole formulation even into memory, for example, on a single machine and things like that. And so, you know, when you hit these size limits, you're still going to need to have some other approach. And generally, you know, the idea is to use some sort of decomposition algorithms where you take this big problem and break it down into a sequence of smaller problems. Okay, so to understand, you know, sort of these decomposition algorithms for stochastic integer programming, we're going to have to just review very quickly a little bit of integer programming methodology. Okay, so this is going to be just a quick review for people who have seen it. If you haven't seen these types of things before, it's certainly not going to be an adequate introduction to the topic, but hopefully it's enough to give you a feel for the types of things that are important as we talk about the stochastic integer programming. Basically, the main idea for solving integer programming problems is you start off by solving a relaxation of the problem. Typically, it's like the linear programming relaxation where you, for example, ignore the integrality constraints on the integer variables. By solving that problem, I'm assuming I'm minimizing for the sake of this discussion. So if I solve that problem where I ignored some constraints, then I'm going to get a lower bound on the true optimal value. It's going to be something sort of, the optimal value is going to be better than what I can truly get. If I get lucky and the relaxation solution happens to be feasible, so somehow those constraints that I tossed out, like the integrality constraints, happen to be satisfied anyway, then I would actually know it's an optimal solution because it's a lower bound and it's also a feasible solution and hence optimal. Otherwise, what you'd have to do is start dividing the feasible region, this is known as branching, by considering different cases, okay? And then you just kind of repeat this process recursively. And so basically by, you know, doing this recursive process, you end up exploring a number of kind of branch and bound search nodes. And the rough sort of timing of this overall process is how long does it take to process a node, for example, to solve that LP relaxation, times the number of nodes you end up having to explore. Okay, so these two factors come in. And both can be very important, right? So for very, very large problems, like in stochastic programming, you have a large number of scenarios, even just solving a single relaxation might be too time consuming, right? By non-decomposition approaches. And so you have to sort of take care of that with kind of decomposition methods. On the other hand, if you don't sort of have strong relaxations that allow you to kind of prune nodes and ignore them from further consideration quickly, then the number of nodes you process could grow exponentially in the size of the problem. And then all hope is lost, right? Of course, if you have this exponential growth, there's no chance the algorithm will ever converge. So we have to take care about both of these things. And so the key to be able to successfully solve any integer programming problem is you have to be able to solve the relaxations fast enough so that time per node has to be pretty fast. But also you have to be able to get strong relaxation so that the number of nodes doesn't grow too large, right? So by pruning high in the tree, you keep control of the number of nodes, and you need really strong relaxations to be able to do that. So one of the ways that in integer programming that we get these strong relaxations is with this concept known as valid inequalities. Okay, so if I'm given a mixed integer set, so I have some linear constraints, I have some variables that are supposed to be integer valued and the rest could be continuous valued. We talk about sort of valid inequalities for the set. So basically it's an inequality, a linear inequality, such that the inequality is satisfied by every point in the set of study. Okay, so that's a capital X. So you might have heard of these as cutting planes or cuts, but basically the whole goal of finding these inequalities and then adding them to your formulation is to try to improve the relaxation bound. Okay, so I add these inequalities after I solve the relaxation with these additional inequalities included. I hope that my bound is closer to the true optimal value. And ultimately, I hope that that leads to then exploring fewer branch and bound nodes so that we don't sort of have explosion in that term there. So questions that people study in integer programming is how to find these valid inequalities, and then how to sort of use them within a branch and bound algorithm. So for finding valid inequalities, just sort of give a very, I'll go back to the generator expansion example to give sort of an idea for where these might sort of come up in problem-specific contexts. We have these variables, remember, that are binary variables. If generator I is open, it's equal to 1. And these yj values are sort of how much demand at location j are being sent from generator I. And in our formulation, we said for each scenario and for each generator, we had a constraint that looks like this. So the capacity CSI is the capacity in scenario S. If xi is 0, then we can't send anything from there, but xi is 1, we send this amount. Okay, and this worked for creating a formulation. But it turns out we can add some additional valid inequalities where we say that the amount that we send, yijs, from I to j in scenario S, can't be more than xi, which is that binary variable, multiplied by this term here, which is the minimum of the capacity of facility I, but also the demand of customer J in scenario S. Okay. So if this capacity is the smaller of these things, then this inequality really doesn't do anything because it's weaker than what we have here. But in many cases, the demand of customer J might be smaller than the overall capacity of a facility I. And in that case, this is not redundant. So when I look at the LP relaxation of this problem, these inequalities might cut off solutions that are not feasible to the LP relaxation when I don't have these inequalities. But on the other hand, they're valid because these are certainly going to be satisfied by every possible integer feasible solution, right? So when xi is 0, then the right-hand side is 0, and I'm not sending anything, which I already knew from this constraint up here. And when xi is 1, then it's saying, well, I can't send more than, let's say, the demand, which is certainly true because why would I ever send more than the demand of a customer to that customer? So there's a valid inequality, and they can potentially improve the LP relaxation. So that's just an example for that specific example. I certainly don't have time to talk about how we find valid inequalities in general. It's a huge topic of research in the integer programming community. But really, the important thing to know is that commercial MIP solvers like Duality, Cplex, Express, you name it, they all have implemented very, very good routines for finding valid inequalities. And so, you know, it's kind of the secret sauce in why many of these solvers are so powerful these days. Okay, so next question is, how do we use these valid inequalities within a branch and bound algorithm? Okay, so this is known as branch and cut. And so the idea is at every node in the branch and bound tree, so you're solving the LP relaxation of that node, that's the first thing you would do. Let's say you get a solution x hat, which you know, certainly might be fractional, even in some of the integer variables. So the next thing you would do, this is again at a node in the branch and bound tree, is I solve what's known as a separation problem, or I try to basically find valid inequalities that would cut off that solution x hat. And the idea is if I can find those valid inequalities, then I'm going to add them to the LP relaxation and resolve it. And I hope that my bound gets, you know, increased from having done that. And then maybe there's a chance I can prune that node. Okay, so that's kind of the process. And you might repeat this at any node in the branch and bound tree. And so why might you do this? Well, first of all, as I mentioned, I mean, you try to add these cuts to improve the LP relaxation value, the bound, and then hopefully you can prune the node and you know, have fewer nodes explored overall. But the second reason, and this is going to be relevant for kind of the Bender's branch and cut method I'm going to be getting to in a minute, is that sometimes you need to add inequalities just to define the feasible region. Okay, in particular, in this Bender's approach that we'll talk about, the number of inequalities that you might need to define the feasible region grows exponentially in the size of the data of the instance. So you can't just write it down. So in this case, you really have to kind of add those inequalities kind of as needed on the fly within this approach here to sort of update the feasible region as you need it. So in general, this idea of adding valid inequalities throughout the branch and bound tree is really at the heart of all modern MIP solvers. Okay, so let's sort of continue on now back to the stochastic integer programming case here and talk about how we can use Bender's inequalities to sort of solve this in a decomposition algorithm. And I'm going to focus here for the most part on the case where the recourse decisions are all continuous. Okay, so you can think of this as an LP relaxation of the true problem that I'm trying to solve. So here the recourse problem is a linear programming problem now. But the first stage might still have integer restriction, so we still need these kind of integer programming ideas to try to solve this. So in this setting, when this second stage problem is a linear program, this QS is kind of a value function. It tells me, as a function of my first stage decision to X, what is the minimum kind of recourse cost? It turns out that function is then a piecewise linear convex function. And a few slides from now, we'll sort of see why that's the case. But the idea then is that what you can do is you have this piecewise linear convex function. And what you can do is when you solve this LP relaxation, or sorry, this linear program, if you look at the dual solution, you can get cuts that sort of support this piecewise linear function at the solution that you passed in when you solved it. We'll see that in a minute. And so what you do then is we construct kind of a main problem, kind of an upper level problem here, where we have a variable theta s that's going to represent the cost of the recourse in scenario S. So we introduce one of these for each scenario. And we just say, okay, for starters, we just say, okay, theta s is greater to the value of that recourse problem. Okay, so this is just a sort of trivial reformulation where I just add these variables theta s, and I say theta s is greater to that. Since they have non-negative weights in the objective, they're always just going to be equal to that. So I haven't really done anything now except add some extra variables. But the idea then is what I'm going to do is instead of adding these constraints explicitly, I'm going to sort of approximate these constraints with linear cuts that I add algorithmically as I go on. Okay, so I'm not going to add these constraints because QS of X is this kind of implicit form here. What I'm going to do instead is I'm going to add Bender's cuts that I find as part of the algorithm. Okay, and again, a couple slides will show you exactly how we get those Bender's cuts, but I first want to kind of show you the general framework for how this works. So what I'll do is I'll have kind of a main problem that's my upper level problem that has the variables X there and those theta variables that I introduced. But then I just have these cuts here that are used to approximate those value functions. Okay. So I solve this main problem. I get a candidate solution, let's call it X hat and theta hat. And then what I do is I go in and for every scenario, I solve a subproblem. And these I can do completely independent of each other because I've fixed my first stage variable. So now they decompose. And then for each one of these subproblems, after I solve it, I'm able to derive a cut. We'll see that in the next slide where those cuts come from. But then I add that cut to this main problem, and I repeat this process until I have no more cuts to be added. And then sort of we know that we've solved the original problem. And so here I want to emphasize that this main problem here is a mixed integer program, right? Every step of the way I'm solving with these integrality constraints here. So I'm solving a sequence of mixed integer programs as I do this. Okay, so finally, where do these Bender's cuts come from? And so under very mild assumptions, we just have to make sure strong duality holds. This sort of subproblem that looks like this, it's a scenario S subproblem where I fixed X hat as the first stage variables. I'll take the dual of that problem. So pi are going to be the dual variables, and those are in the objective multiplied with the right-hand side where this X is now fixed. So that's the whole sort of objective coefficients in this dual problem. And my dual feasible region looks like this. Okay, so those are my dual constraints. And the key thing is that the dual constraints do not depend on X at all. Okay, so this dual feasible region is kind of independent of X. And so what I can do is sort of use kind of this analysis to derive cuts that are good for this particular X hat, but they're also valid everywhere, because that's sort of a key part of this, how this works. So this dual problem if I just let ext of this pi s represent the extreme points of that scenario S feasible region, so there's finitely many of those, then I can consider this dual problem as being the maximum of this kind of finite set of values here, one for each of these extreme points. And so if I get one of those particular finite vectors, then I can add what's known as the Bender's cut, where I just plug that in, and then I no longer have x hat fixed, but I consider it to be a decision variable again. And so this is now a linear inequality in the space of theta s, and my first stage variable is x. So it's valid everywhere because this dual feasible region does not depend on x, and it's going to be tight. It's going to exactly define the objective value I wanted to define at the particular solution x hat that I used to derive that particular extreme point. Okay, so these are the cuts that are sort of showing up in that process that I was showing here. So if I go back here, I just kind of wrote it generically, but this is the form of what those cuts actually are. Okay, so this basic Bender's algorithm, basically it's fairly easy to implement, but what happens is, this advantage of this approach is that every iteration, that main problem, the upper level problem that I'm solving, is a mixed integer program. Okay? And as you add more cuts, that tends to become more difficult to solve. And unfortunately, unlike for linear programming, if I have a mixed integer programming and I changed it in some way by, say, adding cuts, it's not very easy to do a good warm start on that. It's not like I can start off where I left off and expect it to be an efficient algorithm. Oftentimes, it's better to just kind of start from scratch completely. And so that kind of leads to a lot of potentially redundant work there. Yes, so that's a good question, Majid. In this version that I'm talking about here, I am assuming that this main problem is solved to optimality in every iteration. You could certainly talk about variations where maybe you sort of solve it to some approximation and then add cuts and try that, but eventually you're going to have to solve this to optimality occasionally. Let's see. Yeah, so that's a good question, Alexander. I'll talk about these other types of cut generation possibilities a bit later when I talk about some of the extensions and enhancements. Okay. So the alternative to this sort of sequence of integer programming approach is what's known as branch and Bender's cuts, so kind of the main sort of topic of today. And the idea here is rather than solving a sequence of integer programming problems, I'm going to do a single branch and sort of bound process where I'm going to add the Bender's cuts only as needed within that branch and cut process. And so here the idea is, there's kind of two phases here. So in this first phase, what I want to do is kind of do some initialization of that main problem with some Bender's cuts. Okay, so for example, what I might do is just look at the LP relaxation of the main problem. So even the first stage variables, I relax integrality, and I solve that linear program relaxation, and then I try to add Bender's cuts and repeat this process until I add no more Bender's cuts. And then I'm going to keep those Bender's cuts in my formulation. Okay, so I'll talk about the importance of this kind of initialization step in a minute here. And then what I do is I start this kind of branch and cut algorithm where at every node in the branch and bound tree, I solve the LP relaxation. I get a relaxation solution. Just like in standard branch and bound, if that bound exceeds sort of the value of a known feasible solution, I can prune that node. What's new though in this branch and Bender's cut approach here is if the solution is integer feasible. In normal integer programming branch and bound, when you have an integer feasible solution, you used to sort of check its objective value and say, if it's better than something that I know, then great, I update that. But otherwise, I'm done at that node. But in this case, we have to be careful because this solution that I get might not be feasible because in this branch and Bender's cut approach, I haven't added all Bender's cuts, right? I'm adding them only as I need them on the fly. And so this is exactly when I need them. Okay, so when I have an integer feasible solution, I have to go and check to see, does this theta hat really record the cost of the recourse correctly? Okay, so what I do is I solve the scenario subproblems. And if there is any discrepancy, I'll add those Bender's cuts to the LP relaxation and then resolve that node LP relaxation again. Okay, so either at that point it become maybe fractional or maybe now I find no more Bender's cuts. Okay, so that's the key sort of thing that's new about the branch and benders cut approach. If x hat is not integer feasible, then I always have the option to just branch and keep, create new nodes. Or I also could add some benders cuts at that point just to try to improve the LP relaxation, but that's sort of strictly optional. That's only sort of a computational enhancement. And so just as a terminology point here, this step here where I add cuts into my formulation, even though my solution is integer feasible, those cuts have a name that's often used in the sort of integer programming solvers. They're called the lazy cuts. And so it's just good to know that terminology for looking up how to implement these things. Okay, so let's see how this approach works for an example generator expansion problem where I have 3 facilities, 3 customers. I'll assume in this case that the capacity is deterministic. And I'm going to have just 2 scenarios for the customer demands. So 4 customers, and these are the values of their demands in those 2 scenarios. And so what I do is I do this LP relaxation. I do a benders kind of iteration approach to solve the LP relaxation to generate some initial benders cuts. And so I'm not going through the details here, but imagine I have some of these benders cuts for scenario 1, and here are the benders cuts I have for scenario 2. And after having done that process, I have this kind of LP relaxation value. So that's my scenario values, objective values, and this is the X value. Certainly it's fractional, so I have to do branch and bound at this point. At this point, I have a value of 286.5 as my LP relaxation value. So now what I'm going to do, since this is fractional, I'm going to start doing branch and bound to sort of get integer solutions here. And so I load this to my solver. I tell it, okay, this is an integer problem now. I change the variable type to be binary. And then I let the solver go to work. Okay, so for starters, let's suppose that the solver doesn't do any of its own general purpose cuts. So what it does is just solves the LP relaxation, and it's going to branch because I had this fractional solution to start with. So it starts doing branching, and it created a few nodes. And here I'm just going to show you what happens, for example, at node 4. When I solve node 4, where I fixed x1 to be 1 and x2 to be 1, my optimal solution at that point had x hat to be 1, 1, 0. Notice that I didn't fix x3 to be anything, but it came out to be 0 anyway. And so this is an integer feasible solution. Okay. And so this is the key thing that we have to do at this point is this might not be feasible because my objective function value might not be correctly recorded. So this is the point where I have to pause and go and generate these benders cuts, or look to see if there's any violated benders cuts by solving this scenario subproblems. So this is what it looks like. I have 2 scenarios. So there's a scenario subproblem for the first scenario and a scenario subproblem for the second scenario. What I'm doing is I'm plugging into the right-hand sides the fixed value of x hat. So that's these red things here. And then I have my theta changing by scenario. So this is for scenario 1, that's for scenario 2. So that's what changes between the different scenarios. For the scenario 1, turns out I did get a violated benders cut. So I have to add that to my formulation. And scenario 2, I didn't get a violated benders cut. In any case, after solving these scenarios, I get a true estimate of my objective function values, 352.5. So I now have sort of a feasible solution of this value. Eventually, so after doing that, I continue the algorithm after 8 nodes. It does solve the problem. For a 3-variable binary problem, 8 nodes, might not seem very efficient, and I would say it's not. So that's not that great. And what went wrong in this example is that we had poor linear programming relaxations. And so what we'd like to think about is how do we improve this? How do we improve this decomposition approach to improve the LP relaxations? Okay. So one thing we could do is in the version I described there, we only added these benders cuts. We had an integer feasible solution at a node. You can certainly add benders cuts at fractional LP solutions. So that's one thing you can do. But the other thing you can do, which may have much more power, is to use integrality of the decision variables to add stronger cuts. Okay, so in particular, trying to find valid inequalities that aren't implied by the standard linear programming relaxation. Okay. And I want to discuss 2 general approaches for how we could be finding such valid inequalities. So one is to look for cuts directly in that kind of main problem that has all the benders cuts in it. The other thing we could do is add these valid inequalities in the subproblems. Okay, it's kind of 2 different ways of thinking about this, and they're complementary. Okay, so let's first talk about these main problem cuts. So the idea is, in the feasible region of my main problem, I have my original constraints. I have some Bender's cuts that I found throughout this process of the algorithm. And I remember that my variables are mixed integer, right? Some are continuous and some are integer. And so generically, though, this is just a mixed integer set. And so all of the research that we have in mixed integer programming for finding valid inequalities for that, just apply that to this. So there's the, many classes of cuts you could find, apply those cuts and try to improve the LP relaxation. Now, one thing that's sort of a limitation of this approach is these Bender's cuts that I have in my formulation. It's not all the Bender's cuts. It's only the ones I happen to have found in my algorithm. And so you miss out, right? You can't, you might have been able to get a better relaxation if you had more of these Bender's cuts. But, this is sort of what you have available. So you use what you can. Now, the good news is this particular sort of idea of generating these cuts in the main problem, if you're using a good MIP solver, they're going to do it for you as long as you add these cuts as part of the formulation. Okay. That's an important detail. If you're adding these cuts only as like lazy constraint cuts, then the solver doesn't see those cuts until later, and they're not able to make use of them. Okay. And so in particular, this is why it's important to do this initial phase where I initialize my problem with some family of Bender's cuts. For example, that could be by solving the LP relaxation with Bender's cuts and include that there, and include these cuts in the formulation rather than just adding cuts in callbacks. Because by including in the formulation, it guarantees that the solver can make use of those cuts to generate all its kind of general purpose cuts and improve the LP relaxation value. So in that facility location, for example, the initial LP relaxation that I got from adding all the Bender's cuts I could find had value 286.5. But when I gave this to Garobi and said, okay, just do your work with your general purpose integer programming cuts, it improved the LP relaxation value with these kind of main problem cuts to 326.8. Right? So that's getting a long way towards where it ends up being the optimum value is 352. Okay, so that's an important thing to take advantage of with these commercial solvers. Okay, so the other thing you can do though is you can add prop cuts directly in the subproblems, and this is where you might have to do a little bit more work on your own to do this process. Okay. And so the idea here is we look at each individual scenario set. So I call XS to be the feasible region where I include the decision variables of the first stage and decision variables of the second stage, but just for that one scenario S. I have my first stage constraints. I have my scenario constraints for scenario S. And I have possibly mixed integer constraints in both the second and first stage variables. So notice, in terms of this Bender's algorithm, I only talked about Y being continuous, but in terms of these types of cuts, it makes a lot of sense to try to do this when Y has integer variables. So we're going to think about that case here for a second. And so there's lots and lots of approaches that have been studied in the stochastic integer programming literature for how do you generate cuts for these single scenario problems and then incorporate them into this overall decomposition algorithm. But the key point of all of this is we're generating these cuts just for one scenario at a time. We're not generating cuts that link different scenarios to each other. And because of that, we can still apply the Bender's decomposition algorithm basically without modification. And I'll show that then in just a second here. I think I'm going to try to sort of move along with it and maybe not try to answer so many questions right now because I'm a bit running out of time, but maybe we'll have time for questions at the end a bit more. So here's how this idea of using these cuts in the subproblems will work. So as we mentioned, we have the kind of loop where we solve the main problem, we get our LP relaxation solution of that, then we solve subproblems and generate Bender's cuts to update that. So that's sort of our standard process here. And imagine we're doing this on the LP relaxation. So we're relaxing integrality in both stages now. But then what I can do is after having solved the subproblem, instead of just generating Bender's cuts and immediately pass that to the main problem, what I can do is I can take my subproblem solution. So there's a Y hat S associated with the subproblem, and I include with that my first stage solution X hat. And now I have that kind of joint vector X hat and Y hat S. And what I can try to do is generate cuts that are valid for that single scenario set. In this schematic here, generically, I'll let these be those. Okay, so these are cuts that I've added into my subproblem based on doing some separation routine for the mixed integer set, capital XS. And what's very interesting is that I can try to do this even if my second stage, my recourse problem, is totally continuous, as long as my first stage has integer variables, the x hat are supposed to be integer valued, I can still hope to separate cuts and add them to this linear programming subproblem, and it'd still be useful. So this is kind of counterintuitive, but it turns out to work out. And so what I've done then is I added some cuts and I basically changed my scenario subproblem, but I've done it in such a way that it still has this decomposition structure. So I can still apply Bender's cuts, basically looking at this as my whole feasible region, my constraints there, and pass that up to the master problem. And these cuts might be stronger, cut off more relaxation. Okay. So how do we generate these cuts for these single scenario sets? Well, again, you can go to general purpose MIP techniques. Unfortunately, in this case, you might not be able to take advantage of commercial solvers to do this for you because they don't see this formulation, right? You just have this solution, you're trying to generate cuts. So you might have to implement some things on your own in this case. That's kind of the downside of the subproblem stuff. But sometimes maybe you can just use problem-specific cuts or a better formulation. So for example, in this facility location problem, we talked about these valid inequalities, right? And so what I can do is I could include these valid inequalities in my subproblem. And then by doing the Bender's cuts based on that, I can hope that my overall relaxation works is better. And indeed, this works. So if I do this branch and cut approach again, I'll start off by solving that master linear program relaxation. I sort of do my iteration to add Bender's cuts there. The key thing here I'm just showing you, is that when I solve the Bender's subproblem, I'm including these additional valid inequalities. Okay, so my subproblems got bigger because I have these valid inequalities in there. But then I can generate these Bender's cuts in the main problem, and they might be stronger. And indeed, if I go through this overall process, my original LP relaxation bound was 286.5 without these subproblem cuts included. Now the subproblem cuts, with those subproblem cuts, the bound goes up to 332.4. Okay, so that's quite an improvement by adding those very simple valid inequalities into the subproblems. And then remember, I'm not done now because I added these cuts into my formulation. And then the first thing I'm going to do is I'm going to let Gurobi add its own cuts on top of that. And when Gurobi does that, the bound went up all the way to 350.5. And remember, my optimum value is 352. So basically, just with cuts, I closed almost all of the gap and almost need no branching at this point. And so that's the power of combining these subproblem cuts and these main problem cuts together to get this overall better relaxation. Okay, so to kind of recap these two different approaches for generating for sort of Bender's and using for solving a stochastic integer program. So for direct Bender's approach, we're solving a sequence of integer programming problems. It's very easy to implement as long as you can figure out how to generate these Bender's cuts. You tend to solve fewer of the subproblems. That's an advantage of this direct Bender's approach. But the problem is that main MIP problem, as you add more of these Bender's cuts into it, can start to slow down. Okay, so that's a disadvantage there, but at least you're taking full advantage of the MIP solver there. The branch and Bender's cut approach, you're adding these Bender's cuts as needed in the tree. There certainly is more to implement that, but that single tree might eliminate some of this redundant work from solving a sequence of MIP problems. And it allows you to sort of nicely exploit subproblem cuts based on the subproblem structure. Okay, so and naturally, my advice would be try the simple option first, and only go to this more complicated version if the simpler isn't enough to solve your problem. Okay, so very briefly, I'll talk about how do you get an algorithm when you have mixed integer recourse, right? So far the Bender's cuts are only sufficient to kind of define the value function if you have continuous recourse. And so a key challenge here is that this value function now is the value function of a mixed integer program. So certainly you can use Bender's cuts derived from the LP relaxation and maybe with the subproblem cuts, but eventually when you're going to need something more to within this kind of master formulation, this main formulation, to enforce these constraints that theta s is greater to qs of x. And so there's all kinds of research for different problem classes for how you can do that. And you know, if you have pure binary first stage, there's certain cuts that you can use. If you have pure integer first and second stage cuts, you can use certain families of cuts, and in various other cases. But basically, you just need some way to kind of assure convergence in this case. I'd say the most general nice version that I know is a recent paper by Van der Laan and Reminders using something called scaled cuts, which is a very nice way of kind of combining information from different scenario subproblems to lead to a convergent algorithm. Okay, so I'm going to close here. I'm hitting against the time here, so basically, you know, I'll say just a few implementation tricks, and then I'll sort of skip probably the recent direction work part here. But you know, a couple of things I want to highlight here. First of all, is that as I described it, I introduced what's known as the multi-cut version of Bender's, where we have a separate variable theta s for every scenario. And then I add Bender's cut separately for every scenario, because that's what I described. An alternative is known as a single cut method, where I have just a single variable theta that's representing the overall expected value function across all scenarios. And then what I do is, you know, when I add Bender's cuts, what I do is I sort of generate the Bender's cut for every scenario individually, and then I aggregate them together according to their probability weights. And so I get a single cut that sort of brings all the information together. And so the kind of trade-offs between the two approaches, the multi-cut version, because we're adding a lot more cuts and you kind of get recombination of them, tends to converge much faster, many fewer iterations. But then that master problem can get very large because I'm adding so many of these Bender's cuts in each iteration. So the single cut version can keep the size of that main problem smaller because I'm only adding maybe one cut per iteration. And so that's an advantage, but you might have many more iterations. That's kind of the trade-off there. But the single cut method might be faster in particular if solving the scenario subproblem is very fast. And the bottleneck becomes solving that main problem with all the cuts there. Okay, so maybe that's okay to do a lot of iterations then by keeping that main problem smaller. And then you can do hybrids where you sort of, these are sort of two ends of extremes. You can kind of partition the scenarios and have some kind of hybrid methods. Okay, so there was a question earlier about different types of cuts, and so briefly I'll mention about that. So one thing that can be a challenge is even doing that phase one, adding Bender's cuts until the linear programming relaxation is solved can be slow, and so you'd like to maybe have better convergence of that. And so one thing you can do is use kind of a level algorithm or regularized algorithm that somehow helps convergence of these types of methods by preventing solutions in consecutive iterations from kind of jumping around too far. And this particularly can be helpful if you're using kind of a single cut version of the Bender's algorithm to sort of still get reasonably fast convergence, even when you don't have all these cuts that you get in the multi-cut version. But yeah, you also can sort of generate cuts in a different way. So the way you generate Bender's cuts is important. In particular, the better choice of cuts can lead to faster convergence. So somebody in the chat had mentioned that there's these Pareto optimal cuts of Magnanti and Wang. Those certainly are one possibility that can help improve convergence of this process. I particularly like this paper of Fischetti et al. From 2010, which proposed kind of a different subproblem. You just solve that linear program and then you get a Bender's cut. And it's especially useful for problems when you have feasibility cuts. I didn't talk about what that is, but it's kind of an extension of this. But it can often lead to faster convergence. But one limitation of this is it's sort of restricted to that multi-cut implementation. Okay, so I think that's probably where I'm going to leave off here. I have a little bit of information of some recent work with my student Ray Chen on different ways of generating kind of strong cuts for this master problem. So I'm going to sort of skip over that in the interest of not going too much over time here. But I'll just close it up here. And so basically, this branch and Bender's cut method can be very useful for stochastic integer programming. But I want to mention also that's not only stochastic integer programming. Basically, any kind of large block structured mixed integer program, you can try to do decomposition algorithm like this. That's going to look very similar. And so, it's useful more broadly than just stochastic integer programming. I would say that these types of problems are still work to do in terms of research here. It's, I think, an exciting research area. solving these stochastic integer programming problems is still not, I would say, routine, like we might say integer programming problems are routine. And even in that case of continuous recourse, there's still work to do, I'd say. And another sort of, I think, key challenge here is that, there's lots of nice work doing lots of different things, but it's not incorporated into kind of standard software packages. And so I think that's kind of a limitation of sort of adoption of these approaches. So I'll stop there. I'm happy to hang around for more questions, but wrap it up there. Thank you all.
Thank you so much, Dr. Jim. The floor is open for questions.
Hello, Jim.
Hi.
Hi. So many thanks for the presentation. So I've been working on that for quite a while, but never seen such a straightforward and simple way to explain that. So many thanks for the presentation. So my question is regarding optimality cuts or general Benders cuts. So as it happens, I'm trying to prove that some optimality cuts they are indeed valid inequalities. So my question would be, how would you go about improving the optimality cuts are indeed valid and they indeed do converge to the optimal solution? I mean, from what I read from the literature, it suffices to show that if I give you all the set of feasible solutions, albeit millions, but if I give you all of them, and you add one optimality cut or one Benders cut that's tied at the solution, then that suffices to show that they are indeed valid and they do indeed converge to the optimal solution. But my question is, how would you go about it, improving that a valid optimality cut is indeed valid?
Yeah, so that's a good question. I would say in general, it's going to be sort of problem specific and specific to the type of cuts that you're generating. I mean, the method you mentioned certainly is valid for the case when you have a finite set of solutions, and even though it's exponentially large, but it's fine for theoretical verification that it's a correct approach. A challenge with that particular method, though, is it would be limited to kind of bounded pure integer problems, right, where you do have a finite set of solutions. Trying to sort of obtain a set of cuts that's sufficient for a mixed integer first stage problem, where you have not a finite set of solutions, would be more challenging. You need a different technique there. But basically, at the end, though, I mean, it amounts to the same thing. Even though it's not a finite list of solutions, you do need to show that for every possible solution you might encounter, that the cut you add would define the proper objective value. But yeah, again, for the obviously, when there's continuous recourse, the linear programming duality works out very nicely. That it's convenient to do that. But in the more general settings, it's generally much more difficult.
Okay, thank you so much.
There are some questions in the chat. So Masoud wants to know which commercial software, based on your experience, is now more efficient for this approach. Is there any significant difference?
Yeah, that's a good question. There are differences, but I'd say it's hard to predict which particular solver is better for which particular problem you're looking at. They just kind of do things a little differently. And so, depending on the problem, one solver or the other might be better. Definitely, I would say, which is, maybe unfortunate, but, the commercial solvers do tend to be quite a step up from basically any non-commercial solvers that are available. I'd say it's, maybe, unfortunate just because it sort of limits the scale and scope of who can use these methods if it really relies on that. But it is the current state of affairs that the commercial solvers are much, much better than I think any non-commercial solvers that are out there. But among the different commercial solvers, there is, it would just depend kind of on the problem. Let's see. And yes, I'll happily share a PDF of the slides. Oh yeah, so there's a good question, Alexander, about the benders in CPlex. So that's actually an exciting development, and I haven't tried it so much on my own yet. But I mean, I think it's a particularly exciting development because some of the techniques I've talked about in terms of like adding valid inequalities to the subproblems, that's something that a solver, you know, like CPlex could do well, right? Because they have good routines for generating general purpose cuts. And so if they start adopting that and implementing that, you might see quite significant improvements with that approach with their general purpose implementation. So that's pretty exciting. I don't know, I mean, to the extent they're doing that or not. So that I just don't know.
Thank you so much. I also have a question. So I just want to know, what's your suggestion for problems with time-consuming subproblems? Because when we are using branch and benders cut, like in my problem, I understand that I need to solve more subproblems rather than like when compared with the classic benders decomposition.
Yeah, that's a good question. I mean, for problems where the subproblems are very consuming, and that's kind of a limitation, the basic benders version, where you just solve the main problem as an integer program and then solve the subproblems, that might be, you know, a better, more attractive in that, right? Because that tends to solve fewer of the subproblems, because you really only kind of, you know, you're focusing very much on the right to upper level solutions or first stage solutions to be generating those cuts at. Another, you know, potential thing, you know, in that setting is you know, maybe just go back to the kind of schematic of implementation here. Another thing that could be useful is that using the multi-cut method as I've described it here can be useful because when after solving the main problem, I don't have to solve with the multi-cut the subproblem for every scenario in every iteration, right? I could focus on some scenarios, solve the subproblem only for those scenarios, and then add the benders cuts and repeat that process. So that can help a lot. In many cases, there's only, you know, a relatively small number of the subproblems are the ones that are important for generating the benders cuts. And so, you know, you can sort of limit your search to those. There's kind of heuristic methods for how you might, you know, limit the set of subproblems. You know, one implementation I often do is I have sort of you know, in the first iteration, I'll go through all the scenarios and, you know, generate a benders cut for whichever ones I can. And then, but I keep track of which scenarios did I get a benders cut from. So that's a subset of those. And then the next iteration, I'll only, you know, try to generate cuts on those scenarios, you know, and you know, sort of keep filtering that down and keep focusing on the scenarios where I was getting cuts successfully from. And then, you know, once I fail, then I go through the whole scenarios again, right? You do eventually have to go back, but that's kind of a reasonable way to kind of focus only on the scenario subproblems that you need to solve.
But can we do this on integer nodes? Because I know that for integer nodes, we use like lazy cuts, and lazy cuts are like necessary for our feasible region, but, or we can just use it for user cuts on fractional nodes.
So you can use it for lazy cuts, you just have to be careful of the implementation. So, you know, if I focus on a subset of the scenarios, and as long as I find a violated cut, then I add that and I'm done. I'm happy. Then I don't have to go through all the scenarios. But, you know, if I went through that small set of scenarios and didn't find a violated cut, then I have to continue. I have to keep going through the other scenarios. But as soon as I find a violated cut, I can just add it and stop. That's enough.
So just to clarify, so I can start like solving from scenario 1, for example. On scenario 3, I find the violated lazy cut. So I stop and add that cut and redo the node.
Yes, that would be a reasonable thing when solving those scenario problems is very time consuming.
Thank you so much. There are, I think, other questions in the chat.
So David, I'm reading through your idea there. Yeah, it's an interesting idea. I'm not aware of any particular approaches that have been able to take advantage of that to guarantee that you get a valid bound. Basically, you know, generally you just sort of need to be sure you have either a lower bound everywhere or an upper bound everywhere, depending on which side you're trying to do. If you try to mix that, it's just, I think, too hard to predict how much the errors go each direction, unfortunately. I'm not seeing any others that haven't been answered.
I have another question.
Okay.
So I just want to know, what do you think about using generic callbacks in Cplex instead of classic callbacks? By generic callbacks, like we can use a multi-thread option.
Yeah, so I mean, I haven't had much experience with that. I don't often use Cplex that much. But it sounds to me it's just the main potential advantage of that is to be able to still allow multiple threads. And so, probably I imagine Cplex implementation, it has to be different to be careful that you allow multiple threads. And so that's why they have the different callback there. I guess if, having available many parallel, sort of threads and processors that can process those threads is important for the performance of your method, then yeah, that's something you probably would want to take advantage of. But I assume that the trade-off is that different type of callback might be more restricted in what you can do. And so it's just a matter of if that extra restriction affects your method or not.
For my problem, I wanted to use generic callbacks because my sub problems are time consuming, and I wanted to solve the sub problems like in parallel. Mm-hmm. To save time. I also tried the option that when I find the first violated cut, so I stop and don't solve the other sub problems, but for some reasons I didn't reach the same solution. So that's why I thought, so for myself was that because I need to add all the feasible cuts, so it's not a correct idea to stop the lazy callbacks. So I should go and try it again.
Yeah, I think in theory, as long as you're adding a cut whenever, just one cut is enough when there's a violated one, you should end up with the same answer. Yeah.
So also, if no one has a question, so for my last question is that the phase one cut generation, so we should just like relax the integrality and solve the classic Bender's decomposition to find those cuts, or there is another way of generating those cuts?
Yeah, so that's a good question. So one way is, like you just said, you relax integrality and do the Bender's on the LP relaxation. But another possibility is if you have some good heuristic algorithms for finding feasible first stage decisions, then you run that heuristic algorithm, you get a first stage decision that's, say, integer feasible, and then generate the Bender's cuts at that solution. So, that would also generate some Bender's cuts that you could include in your initial formulation as well. Those are probably the two ways that I can think of that would be reasonable for that.
Thank you so much. So because these cuts are because you said that we find integer solutions and then we cut Bender's cut based on integer solution, do they have better relaxation?
So for the bound that you get at the LP relaxation itself, they won't be better in that sense, because really you just need the cuts that are needed to eventually get to the LP relaxation bound. But it's possible that then when you go off and the solver adds its kind of integer programming based valid inequalities, that you might get better results. It's hard to predict that. It's not something that you could be said, definitively. But I think, there's a good chance that having those cuts that you got at integer solutions might be helpful for getting better cuts after that process is done. But would it only be something you could observe empirically.
Thank you so much. So I'm wondering if there are more questions. Thank you so much, Dr. Jim. And also I want to announce that in June, we will have a networking event for MORSC because May is our 6th anniversary. And we wanted to celebrate it today, but because of some COVID restrictions, we couldn't reserve a place at university. So we deferred the networking event in June. So stay tuned for our emails.
Thank you all very much. Excellent questions, a very engaged audience. It's great to see such an active group there. So yeah, I'll look forward to meeting many of you in person someday, hopefully. So thank you all.
Thank you. Have a good one.
Bye.
Bye, everyone.